In this section of Chapter 2, we're going to take a look at the inverse of a matrix. Now, when I talk about the inverse of a matrix, what I'm talking about is the multiplicative inverse of a matrix, okay? So we're talking about the multiplicative inverse here. And if you remember back from our days of thinking about the real numbers, every real number other than 0 has a multiplicative inverse. So for instance, something like 7. If I multiply that times 1/7, I get back 1. And we know that a multiplicative inverse is a number, well, I'm sorry, over the real numbers, a multiplicative inverse is something that you multiply by to get to 1. And so what we would do is we'd say, well, 1/7 is 7 to the negative first power. So 1/7 is the multiplicative inverse of 7. All right, so that's what multiplicative inverse did over the real numbers. Now, additive inverses are pretty straightforward. Additive inverses are just the negatives of the numbers. So if you want to add two numbers, and their inverses should add up to 0. But when I talk about multiplicative inverse, I need numbers that multiply to give us 1. Now, as far as matrices go, the 1 of the matrix, or of matrices, is actually going to be the identity matrix. Because as we saw last time, if I take the identity matrix and multiply by a matrix, in this case 2, 4, 5, -1 times the identity, well, when I do my row column expansion, 1 times 2 plus 0 times 5, I just get back 2. Then I do 1 times 4 plus 0 times -1, I just get back 4. Similarly, 0 times 2 plus 1 times 5 gives me a 5. 0 times 4 plus 1 times -1 gives me a -1. So the identity matrix is the sort of 1. It's the thing you multiply by and don't change any matrices. Okay? So when we're looking to get multiplicative inverses, I basically need to multiply to get the identity. All right? And that's what we say. We say the inverse of a matrix is another matrix, which we denote by a to the -1 power. And if a has an inverse, which we call a to the -1, then it's going to look like this, and it's going to multiply a times a inverse gives you back the identity matrix. And by the way, it's going to be necessary. We're only going to deal with square matrices here so that you can multiply on both sides by the inverse of a. So a times a inverse is equal to a inverse times a, which is all equal to the identity. All right. And again, in this chapter, all of our a's are going to be square matrices. So the multiplicative inverse of a matrix is what is another matrix that you'll need to multiply by to get the identity. Now I want you to just calculate and multiply a times c, and then multiply c times a. Go ahead and push pause on the video and see how that turns out. Okay, so basically what we're doing is we're taking a and c. First time I'm going to multiply a times c, and then I'll switch the order and multiply c times a. So first a times c. Again, row column expansion, 3 times 7. So 3 times 7 minus, well, I should say plus 4 times -5. All right, so that's my first row, first column. First row, second column, 3 times -4 plus 4 times 3. Then we go second row, first column, 5 times 7 minus, or I should say plus 7 times negative 5. Thinking of doing that in one step. And then lastly, 5 times 7, excuse me, 5 times negative 4 plus 7 times 3. Again, we went over multiplication of matrices in the last video, so it should be pretty straightforward. So that's what we get when we do our row column expansions. Now notice what's going to happen. 3 times 7 is 21, plus 4 times negative 5, that's a negative 20. 21 minus 20 is just going to give us a 1. 3 times negative 4 is negative 12, plus 4 times 3, which is positive 12. So negative 12 plus positive 12 gives us 0. Similarly, 35 minus 35, oops, gives me a 0. And then this is negative 20 plus 21 again. That gives me a 1. So when you multiply A times C, you do get back the identity matrix. Now let's check that you do that the other way as well. So let's multiply C times A. I'll do this a little bit quicker. 7, when I do row times column, 7 times 3 is 21, minus 4 times 5, so that's a minus 20. 21 minus 20 is a 1. 7 times 4, 28, minus 4 times 7, so 28 minus 28 is 0. Negative 5 times 3, positive 3 times 5, that's going to give you negative 15 times, plus positive 15, that's going to give you another 0. And negative 5 times 4 plus 3 times 7, that's negative 20 plus 21, gives you a 1. All right? So in that case, what we see is that these two matrices are inverses of each other, okay? And again, what we would do is we'd say, well, A inverse is C, or maybe I should write it the other way. C is A inverse. And also, A is C inverse, right? For the exact same reason, okay? So these two matrices are inverses of one another. Okay, so anytime we get a matrix where I can multiply A times C and then multiply C times A and get the identity, we get those two matrices are going to be inverses. Again, I do emphasize here that we are dealing with square matrices. It won't make sense to deal with inverses if your matrices are not square. Okay. I want you to calculate these two and just decide if C and A are inverses of each other. Push pause on the video. All right, so let's go ahead and multiply these. First off, I've set up our new A and our new C. So our new A times C, 4 times 1 plus 3 times negative 1, that gives me a 1. 4 times negative 1.5, that's going to give me a negative 6, plus 3 times 2, that's going to give me a positive 6. So negative 6 plus positive 6 is 0. And then 2 minus 2 gives me another 0. And then lastly, 2 times negative 1.5 is negative 3, plus 2 times 2 is 4. So negative 3 plus 4 gives me a 1. So yes, I do get the identity when I take A times C. When I take C times A, it turns out, I'll save us a little bit of time, that we should wind up with the identity here as well. All right. So A times C and C times A give us the identity, and therefore what we can say is that C and A are inverses of each other. Now, the majority of this section isn't determining whether two arbitrary matrices are inverses of each other. In fact, these are two very, very special cases in that they are. Most matrices are not going to multiply and give you out the identity, right? If you just picked at random, random numbers in a matrix, you're not going to get the identity when you multiply. But these are special cases. So it sort of begs the question of how do we find the inverse of a matrix? And we're going to have basically three different methods for finding the inverse of a matrix and figuring out if the inverse even exists. The first method is going to be exclusively for 2 by 2 matrices. Okay? So if we have a 2 by 2 matrix, which we will call capital A, and the entries in the first row are A, B, and the entries in the second row are C, D, then the inverse will be this number times this matrix. So it's going to be a scalar times a matrix. This scalar is going to be a fraction, 1 over AD minus BC. And then notice kind of how this goes for the matrix. We swap the main diagonal, and then we put minus signs on the other two numbers. Okay, so we do swap the main diagonal, put minus signs on the other two numbers, and then we multiply by that constant there. Now, this constant that shows up in the denominator of that 2 by 2 inverse is called the determinant of a matrix. So notice here we had AD minus BC. The way most people remember that is they remember it by saying we're going to multiply the main diagonal and then subtract the other diagonal, or excuse me, the what we would call off diagonal. All right. So A times D minus B times C. Okay. So that thing is the determinant. Now think about what that meant here. Okay. This will always be the inverse of this matrix. However, what's going to happen if AD minus BC is 0? Well, then we get a situation where it's a 1 over 0 as my scalar out front, which is an undefined situation. So if we get an undefined situation, what that means is that there's actually no way to get an inverse. So if this denominator here, AD minus BC, is 0, then there's no way to find an inverse, and we're kind of stuck. So let's scroll to this example, or these two examples here. Let's find the determinant of these two matrices. I want you to push pause on the video and try to find the determinant, AD minus BC, and then tell us if, based on that determinant, if an inverse exists for that matrix or if it doesn't. So let's go ahead and do that. I'm going to do this for that top matrix first. So what is the determinant in this case? The determinant of our matrix. Actually, I'll just call the matrix M. Hopefully that doesn't throw us off. The determinant of matrix M is going to be AD, that's 5 times 9, minus BC, 7 times 6. So or it doesn't matter if you write 6 times 7 or 7 times 6, it's all the same. And what that gives me is the number 3. Now, because this determinant is 3, we know the inverse exists. And in fact, we know how it exists. What's going to happen in order to get our matrix to have an inverse, excuse me, in order to find the inverse of the matrix, let's call this to the inverse. We're going to go 1 over my determinant, which is in this case 3. And then if you remember what happens, the A and the D swap. So the 9 and the 5 would swap. That 6 would turn into a negative 6, and that 7 would turn into a negative 7. Now, I don't expect you to memorize, the 2 by 2 determinant formula. In other words, I don't remember, no, I should say determinant. We will have to know the 2 by 2 determinant, but I don't expect you to memorize, swap the main diagonal, negate the off diagonal. But it is something kind of useful to know. All right, but you should know how to calculate the determinant. We'll see more of the determinant in chapter 3. Okay, we'll take a more in-depth look at the determinant in chapter 3. So anyways, that is the inverse of the matrix. Now, if you wanted to, you can actually multiply the scalar of 1/3 times everything, and you'll find that the inverse of the matrix could have also been written, well, 9 times 1/3 is 3. Negative 6 times 1/3 is negative 2. Negative 7 times 1/3, well, there's not a whole lot of that. Negative 7/3, I guess. And then 5 times 1/3 is going to be 5/3. Is about the best way I can write that. So this here is the inverse of that matrix there. Okay, using what we know about 2 by 2 determinants and the determinant's connection to the inverse. If we scroll down and we take our next example, well, our next example is going to have determinant of, we'll call it, I don't know, matrix K. Again, we can use whatever letters we want here for our matrices. The determinant of K, so we're going to take negative 8 times 1, and then subtract negative 2 times 4. Okay, notice what that's going to give me. That's going to give me a negative 8, and then negative 4 times negative 2 gives me a positive 8. So minus 8 plus 8 gives me 0. Now, the determinant of this matrix being 0 means that there is no inverse. This inverse doesn't exist because this matrix would be undefined. We can't divide by 0. So that's what we know about inverses. Now notice something. This matrix, negative 8, negative 2, 4, 1, we said it does not have an inverse. Okay? The only number in the real numbers that does not have a multiplicative inverse is 0, right? We found a matrix, which was definitely not the all zeros matrix, but it did have a determinant of 0. So what we're ending up with is that there's actually a whole class of matrices, there's whole classes of matrices where the inverse doesn't exist. So let's take a look. We're going to look at some other neat properties of inverses, and that'll lead us to another method of finding the inverse. Notice that our method of finding the inverse only worked in a 2 by 2 case. What if we wanted to go up to the 3 by 3 or a 4 by 4? So we're going to look at those things in just a second. First, I just want to point out some properties of inverses. Well, the obvious is are the first two. If A is invertible, then the inverse of A is also invertible, and that's fairly obvious because A times A inverse is equal to the identity. So A inverse has an inverse, which in fact is A. All right. So if you take the inverse of A and then take the inverse of that, you get back to A. So inverse of an inverse is just back to the regular matrix. Now, the second property is a little bit harder to understand without an example, but we have AB inverse. When we take the inverse of a product of two matrices, it's going to be the inverse of the second matrix multiplied times the inverse of the first matrix. Now, this is sort of colloquially referred to as the socks and shoes property of inverses. Let me explain what I mean by that. Whoops. So let's go back to let's say A and B are both invertible matrices and that the inverse exists. Okay? What that inverse is telling you is that if you multiply the product AB times its inverse, you should get back the identity. Okay? But how would you multiply AB times, well, let me say it this way. What else do we know that multiplies AB that gets us back to the identity? Well, if you take AB, A times B, and then multiply by B inverse times A inverse, what's going to happen is you can rewrite that based on the associativity property of matrices. We saw that last time, the associativity of matrix multiplication. And so what we can do is we can move our parentheses around. As long as the A, B, B inverse, A inverse stays in the same order, we can rewrite this. We can say, well, actually, I wanted to multiply the B times the B inverse first, and then after I do that, multiply times A inverse. Whoops. Notice what that's going to do. That's going to give us A. B times B inverse is the identity. Then A inverse. A times the identity is just A by itself. So we got A times A inverse, which is obviously the identity matrix. Let me scroll that up. So because AB times this gives you the identity matrix, this matrix has to be equal to AB inverse. So you can't just distribute the negatives because you have to be aware of the order. Now, why this is called the socks and shoes property is because we think of A and B being two functions, right? Or two processes. And if you think about putting on your socks, we'll call that A, and then putting on your shoes, we'll call that B. If you want to undo that, so you put on your socks, then you put on your shoes. If you want to undo that, you're going to have to take off your shoes first and then take off your socks. So putting them on is like multiplying by A and then multiplying by B. Taking them off is like multiplying by the inverse of B and the inverse of A. Okay? So again, if I put on my socks first, then my shoes, in order to undo that process, I have to take off my shoes first and then take off my socks. So that's where it comes from, the socks and shoes property. But it's basically saying that the inverse of a product is the inverses of each piece, but in reverse order. And by the way, you could do this for any number of matrices. You just have to reverse the order. Now, here's why inverses are nice. Let's take the matrix equation AX equals B. Well, if AX equals B, let me put it this way. If A has an inverse, so if A is invertible, then what we can do is we can multiply both sides of this equation by A inverse. A inverse times A gives me the identity. The identity times any matrix is itself. And so we can solve the equation by multiplying both sides of the equation by A inverse, and that will give us the X. Again, here X and B are vectors, and A is a matrix. So we can solve equations utilizing that trick. And this is also going to give us the way that we can find inverses an algorithm to find inverses when our matrix A is 3 by 3 and 4 by 4 and such. We'll see that in just a moment. But I just wanted to give you, that's why these inverses are nice, because now we can use this A just like we would use a coefficient, a real number coefficient. It's sort of like saying if I'm multiplying A times X and getting B, well, how can I get X? I can, in the real number sense, divide by A. We don't have a division here in matrix sense. So in the matrix sense, we have to multiply times A inverse. And so we can solve every matrix equation utilizing the inverses so long as A has an inverse. So I want you to go ahead and do that. I want you to start by using the method we saw before to find the inverse of 4, 6, -1, -2. Notice I used the same matrix in both equations. So find the inverse of that using the 2 by 2 method we did before. And then once you find the inverse, solve the equation by saying, well, multiply times A inverse on both sides. Go ahead and push pause on the video and try to do that. So, take the matrix times X equals 7, 5. The first step is to find the inverse. Now, the inverse is going to be, well, I'll just call it this. I'll shorthand 1 over the determinant. Oops. 1 over, I'm not putting 9 there, but 1 over the determinant multiplied by the following matrix. If you remember what we do, we swap A and D, so that will become a -2, that will become a 4, and then B and C we just negate, so that'll become a -6, that'll become a +1. Now what's the determinant? I'm getting 4 times -2, that's -8, minus -1 times 6, so I get -8 plus 6, so I get -2. So I got a determinant of -2. Again, that's AD minus BC. I'm going to distribute that -2 into all of the terms to figure out the inverse, the actual inverse of the matrix. So what I'm getting is a 1, 3, -0.5. I'm going to call that -0.5 just to save some room on my space, and then -2. All right. And if you wanted to double check that this was the actual inverse, just do a row column expansion. 4 times 6 times 1 times -0.5. You get a 1. 4 times 6 times 3, -2. You get a 0. -1 times 1, -2 times -0.5. You get a 0 again. And then -1 times 3, -2 times -2, you get a 1. So you do get the identity when you multiply, but that's the algorithm we used before. So that's the inverse. And what this means is, in order to solve the equation, all I have to do is, actually, let me rewrite this equation here. I'll do a intermediate step. All I have to do is take this inverse and essentially multiply it on the left-hand side and on the on the left-hand side of the left-hand part of the equation and on the left-hand side of the right-hand part on the equation. Notice I am, on both of these, I'm putting this matrix on the left side, okay? And what happens is that the inverse times this matrix is just going to end up as the identity. We just mentioned that, so you're going to get the identity matrix times x. Well, the identity matrix times any matrix is just your x. And then we can multiply this matrix times this vector and get out a solution for x. So we get x equals, now this is a vector. If you wanted to do a vector expansion, 7 times this column plus 5 times that column, you could. If you wanted to do a row column expansion, again, the vector is just a special case of a matrix, so you can do a row column expansion too. So 1 times 7 plus 3 times 5, I think I got a 22 there. And then -0.5 times 7 minus 2 times 5, I got a minus 13.5. Hopefully, again, I did that right. I am double checking my answer. Yeah, I got -13.5 on my calculator. And again, if you wanted to check and see if you've done all your calculations right, you can obviously plug it back into this top equation and see if you take 4, 6, -1, -2, multiplied by 22 and -13.5. In other words, if you replaced x with that vector, do you in fact get out 7, 5? And again, I'll just check that real quick. 4 times 22 plus 6 times -13.5 does in fact give me a 7. and then -1 times 22 minus 2 multiplied times -13.5 does in fact give me back a 5. All right, so the answer to that original equation, this equation, was 22 and -13 was the vector 22, -13.5. Now, the nice part about solving this equation and then going ahead and saying, well, actually, I wanted to solve that other equation. That other equation had a outcome vector of -1, 4. Okay, and now that I've already found the inverse of 4, 6, -1, -2, I found the inverse is this. Now I can say, well, in order to solve that equation, all we're going to do is say, well, x has to be the inverse multiplied now instead of instead of 7, 5, I got to multiply it by -1, 4. And that is going to give me a vector, which hopefully, if I've done this right, 1 times -1 is -1, plus 3 times 4 is 12, -1 times, -1 plus 12 is an 11, and then -0.5 times -1 is a positive 0.5, -2 times 4 is a -8, so we're getting a -7.5. And once again, if you wanted to check it, try to plug it in here and see that you get -1, 4. And when I checked that, yes, it did give me an answer. Now, I want you to notice something about these inverses. Make this observation. If A is invertible, then no matter what your vector B is, as long as it's the right size, obviously, I can always apply that trick. So if A is invertible, then the A inverse is going to exist. So no matter what the B is, I can apply that trick. That means AX equals B always has a solution, all right? AX equals B always having a solution, we saw that that meant there has to be a pivot point in each row. And the only way to get a pivot point in each row, if it's a square matrix, is to row reduce to the identity, all right? So the row reduced echelon form of this square matrix must be the identity if we have an inverse. So if we have an inverse, then the row reduced echelon form is going to be the identity. Again, we're only talking about square matrices here. So we always have a solution. Therefore, we need a pivot point in each column, in each row. And therefore, we're going to row reduce to the identity. Again, think about how things would have had to row reduce in order to have a pivot point in each row, as long as it's a square matrix. Okay, it has to be the identity. All right, so speaking of row reduction, now that we've seen how matrices multiply, we're going to introduce a concept called an elementary matrix. Now, an elementary matrix is going to be a matrix where if I multiply it by a matrix A, it is equivalent to performing an elementary row operation on matrix A. So for instance, if you look at this matrix E1 here, generally speaking, the elementary matrices we denote by capital E subscripts. So if I look at this matrix E1, if you think about what the multiplying, if I take E1 multiplied times A, it's going to keep that top row as constants. It's going to keep the middle row as constant. And to the last row, it's going to take a -2 times the top row and add to the bottom row. So it's going to replace the bottom row with -2 times the top row plus the bottom row. Let me actually do that once, just kind of do the multiplication by hand. Take that elementary matrix, what we called E1, and multiply it times some arbitrary 3 by 3 matrix. Since we're going to be dealing with square matrices most of the time, that's what's going to happen. So notice what's going to do. If I expand first row, first column, you're just going to get A plus a bunch of zeros. First row, second column, I get B with a bunch of zeros. So what I'm getting out there as a product in my first row is I'm just getting the first row unchanged. So I'm getting A, B, C unchanged. Same thing with my second row. If you think about second row times first column, you're just going to get a D plus some zeros. Second row times second column, you get an E plus some zeros. Second row times third column, you get an F with a bunch of zeros. So you get D, E, F. So this 1, 0, 0 basically gives you back the first row. The 0, 1, 0 gives you back the second row. And then notice what -2, 0, 1 is going to do. It's going to take -2 times A and then add 1 times G. Lost that. Then I get -2 times B and then add H. And then -2 times C and then add I. And if you think about what that's equivalent to, that's equivalent to taking this top row, multiplying it times a -2, taking the bottom row and replacing the bottom row with that. So that's our row replacement. That is our row replacement elementary row operation. Okay, so -2 times the top row plus that bottom row, replace it. So by multiplying that matrix times this, we did an elementary row operation. And we could easily get any other row replacement by just putting the right numbers in the right spots here. All right. Now, what are the other two elementary row operations? We had our row replacement. That was one of the big ones. Another one was swapping rows. Well, if you swap rows, it's kind of like I took the identity matrix and I just swapped the rows in the identity matrix. And if you, I'm not going to do this one, but you'd preserve row 1 and then row 2 would now, well, row 2 and row 3 are going to swap. That's what I'll say of your A. So your row 2 of your new matrix is going to be your original row 3. And then the last elementary row operation is multiplying by a scalar, and that would be something like this. We just take we take the identity and we replace one of the ones with whatever scalar I want to multiply. So this would have the effect of multiplying the second row by the number 3 and leaving the top and the bottom row the same. Now, not fun fact, it is a fact. I don't know how fun it is, but it's a fact that every elementary matrix that we could possibly imagine is invertible. Okay, it's gonna have an inverse. And That's pretty obvious once you think about it, because every elementary row operation can be undone through another elementary row operation kind of in reverse. Okay, so you can um, undo an elementary row operation if we'd like. So if I go back to this one, if I wanted to undo this, I could take a positive 2 times this top row and then add that result to this one, and you'd see that 2a minus 2a would get canceled out, 2b minus 2b would get canceled out, 2c minus 2c would get canceled out, and you'd just be left with your original matrix with GHI on the bottom. So because every elementary row operation can be undone, all of the elementary matrices are invertible. Okay. Now let's put some things together that we talked about. So let's take an arbitrary matrix A. We know that if A has an inverse, then it's going to row reduce to the identity. We're going to say A is an n by n matrix. That's why I'm using sub n there. The identity, which is the n by n identity. So we know that if A is invertible, if A has an inverse, it row reduces the identity. Now we know that row reduction is just multiplication by a bunch of elementary matrices. So we know that there are some elementary matrices which represent this row reduction, which when we multiply them by A, give me the identity. Now think about what these elementary matrices have to do. If you take the product of all of these row operations, all of these elementary matrices, that product is multiplying by A and giving us the identity. That means that product here is in fact the inverse of A. So the inverse of A is just going to be the elementary matrices which row reduce to give us the identity. All right. Now, how can we use that fact? Well, we can use that fact if we know each one of these row reduction matrices, we could multiply them all up and find the inverse. Or we could create an algorithm that sort of keeps track of all of these matrix operations. By the way, you'll notice that I've labeled this E1, E2, E3, kind of going from right to left. That's because when you do row reduce A, you do, the first elementary row operation that has to be done is going to be represented by E1. That's the first multiplication. And then the next elementary row operation will be E2. That's my next multiplication, and so on and so forth. So that's why they're in that order, because of the order where you're going to have to row reduce the A. But if we can keep track of these elementary matrices, then we can find A inverse. Okay? So that's the goal, is keep track of the elementary matrices, and if we can keep track of the elementary matrices, we're going to find the inverse. Now, this leads us to an algorithm. This leads us to a nice way of finding A inverse. And basically, what we do is we create if A is an n by n matrix, we double the number of columns. So we're going to put a gigantic matrix in. We're going to take A as the first n columns, and the next n columns are going to be the identity. So we have this really big n by 2n matrix. And we're going to put that really big matrix in row reduced echelon form. Now here's the trick. Because we're putting it into row reduced echelon form, I know that A is going to row reduce to the identity. So every single A, if A has an inverse, is going to be row reduced to the identity. And because each row reduction was just a multiplication of some elementary matrices, when I take those elementary matrices and I multiply them times this part of the matrix, so you do those same elementary matrices on this and this part of the matrix, well, if I take the elementary row matrices, multiply them times the identity, then what I'm getting here is just a product of those elementary matrices, which we know is going to be A inverse. So when A inverse exists, we can utilize this algorithm, create this big matrix, which we're going to be as A and then I, row reduce it, and you'll get the identity along with A inverse in the second half. Take a minute and think about that and or figure that out if you haven't yet. But basically, what row reducing this big ol' matrix does is it keeps track of these elementary operations, which caused A to reduce to the identity. And then if I do these elementary row operations multiplied times the identity, I'm going to get A inverse. So on the first half of my matrix, when I row reduce it, I'm going to get the identity. On the second half of my matrix, I'm going to get the inverse. Now, I will say this one little caveat. That's if the inverse exists. Remember, there are matrices where inverses do not exist. We've seen those before. And if inverses don't exist, then A is not going to row reduce to the identity. So this algorithm will not only give us the inverse, but it will also tell us when A inverse doesn't exist, because the first half of this matrix is not going to row reduce to the identity. So let's go ahead and use the algorithm to find the inverse of this matrix here. This is a 3 by 3 matrix. Notice we could not have utilized the thing we learned before, because the thing we learned before was only for the 2 by 2 case. Now, you can push pause on the video if you'd like. Try to do that if you understand it. Otherwise, I will do this in about 4 or 5 seconds. So here's what I would do. Okay, we are going to grab our calculator and we're going to create a really, really big matrix. Okay, the matrix that I was using, the matrix which I called A, I think I'll use a different letter. I'll use matrix C. The matrix I called A was 3 by 3. So what I'm going to do is I'm going to create a 3 by 6 matrix. Now, the first 3 by 3, the first half of this matrix is going to look like the matrix we dealt with before. So the first 3 columns are going to be 0. Well, let me write this down. It's probably easier just to say it than to write it down than to actually say it. So my matrix First three columns are going to be that 0, 1, 4, 1, 0, negative 3, 2, 3, 8. So that's my A part. Now I'm going to go to my next three columns and I'm going to create the identity matrix. Hopefully, oops, let me scroll that. So hopefully you see that, and the next three columns are going to be just the identity matrix. Okay, let's go back to the home screen and see if we can, I don't know if this one will display nicely, but yeah, there it is. It displays nicely. So first half of the matrix is the A I'm looking at. Second half is the identity. And so then I go into my math menu. I want to put my matrix C into row reduced echelon form. And here's what I can tell. Two things at once. First off, I can tell that my original matrix was invertible because in this first half of the matrix, we have the identity. And not only is that, but I can tell that the inverse of the matrix is the second half of my, what I'll call the mega matrix, right? So my row reduced mega matrix here, the second half is my inverse. So what this means, again, just restating what I just said, is that my original matrix, this was my original matrix, 0, 1, 2, 1, 0, 3, 4, negative 3, 8, does have an inverse because the first part row reduced to the identity, and moreover, the inverse is that second part, okay, of the matrix. And if you wanted to, you could go ahead and do the row column expansion and multiply and confirm that you actually do get the identity matrix. It's not terribly hard to do. You can just go ahead and do it, but I'm not going to show you that. You can do that for yourself. Check for yourself if you'd like that this in fact is, when you multiply it, you multiply the top matrix times the bottom matrix, you actually do get the identity. All right. Now let's do that algorithm for the 4 by 4 case. I want you to push pause and try this 4 by 4 case. See if you can see if first if it's invertible, and then see what the inverse is. All right, so what you do again is you put this matrix in your calculator along with sort of, well, I shouldn't say this matrix in particular. You're going to make a 4 by 8 matrix where you put this matrix as the first 4 columns and then the identity matrix as the next 4 columns. Now, when you row reduce this matrix here, it turns out that when you row reduce that big mega matrix, and we don't have to row reduce the whole thing, or I don't have to state, when you row reduce, the first 4 columns give you what looks starting out promising, looking like the identity, but then a row of zeros here in the first 4 entries. Okay, you'll get something there. But notice in these first 4 entries, you end up with a free variable, which means that original matrix that we were dealing with does not row reduce to the identity, and therefore that original matrix we were dealing with, this one, is not invertible. Okay? So this one is a 4 by 4 matrix which does not have an inverse, precisely because it does not row reduce to the identity, and we saw that through the algorithm that we were dealing with. So not invertible, and we saw that by using this sort of what I'll call the mega matrix algorithm, putting in a matrix A alongside with the identity and row reducing it. Now I want you to use one more, uh, use the algorithm one more time to find the inverse of this matrix if it exists. Hopefully you went and did that, and you're going to see your inverse is a pretty ugly matrix, but that this does have an inverse. So you put in this 4 by 8 matrix, which is this matrix alongside the identity to the right. You put that in row reduced echelon form. You do get back the identity in the first 4 columns. So when you put that in row reduced echelon form, you row reduce this, you get back the identity in the first 4 columns, and your next 4 columns, well, I put mine all in improper fraction form. Actually, let me go back a little bit. Yeah, there we go. I put mine in improper fraction form. So that's just hitting the fraction key on your calculator. So you hit math and then frac, and that'll put everything in a fraction form. This is the fraction form. Uh, this is improper fractions. Some of you might have gotten out mixed numbers. That's fine too. But the point is that this matrix here has an inverse, and moreover, that inverse is this. And this is probably the nicest way, one of the nicest ways to find inverses utilizing your calculator and the row reduced echelon form of your calculator. All right. Now I want you to, so we found 2 methods so far to find inverses. Our first method utilized this equation or this thing. If it's a 2 by 2 matrix, then we can find the inverse utilizing this. By the way, doing what we just did using the row reduction algorithm, we could have found inverses for, or I should say an inverse for this matrix, and we would have found out that this matrix does not have an inverse, just like we did before. Okay, so you can use your row reduction algorithm on 2 by 2 cases, and you will end up with the same thing. So we did our row reduction algorithm. We did, excuse me, so we did the 2 by 2 case, the special case. Then we did the row reduction algorithm. And actually, there's one other way to find the inverse of a matrix. And that's just by trying to get our calculator to compute this directly. All right. In fact, there's an inverse key on our calculator to find inverses. And it's a pretty straightforward key once you know where to look for it. So here's what we're going to do. We're going to do the 2 of the problems that we just did, but we're going to use the inverse key rather than doing the row reduction algorithm. So we're going to try to find the inverse of this matrix: 0, 1, 2, 1, 0, 3, 4, negative 3, 8. Okay? Now, what I did, I have that was my matrix when I used from before, that I had put into matrix C on this calculator. So I'm going to go back to the matrix menu and I'm going to edit matrix C. And we want to keep these first three columns the same. So we're going to keep the first three columns the same, and we're going to forget about the identity part of that matrix. So we're just going to change C into a 3 by 3 matrix, or put it in. By the way, if you've already erased yours, just go ahead and put this in 0, 1, 2, 1, 0, 3, 4, negative 3, 8. Go back to the home screen. Let me clear that out. And then what I do is I say go to the matrix. We're using matrix C. And then remember how inverse was always to the negative 1 power? Well, we can just hit the hit this button here. It's highlighted in red. That is going to give us the negative 1 power. Hit enter, and sure enough, we get the exact same inverse that we had before. All right. Now, so this is just a straightforward button on our calculator, that negative 1 exponent. Our calculator knows that we should do inverses when we have the negative 1 exponent on a matrix. All right. Now, let's also go to this one, the 4, 2, negative 1, 7, 0, 3, 9, 2. If you remember, this matrix was the one that did not have an inverse. Okay, I put this matrix into, I believe it was matrix B on my calculator. Yeah, there it is, matrix B. So just to remind you what we did earlier, we row reduced the matrix B, and the first four columns were not the identity. Therefore, we know that this is not invertible. The original matrix, the original 4 by 4 matrix was not invertible. Okay, so first four columns are not the identity. We had this free variable. We know we're not invertible. Now, if we wanted to do that a little bit more directly, what we could have done, could have edited that. Let's create a 4 by 4 matrix. So throw out the identity part. Now my matrix B is exactly the matrix I had before. So it's exactly my original matrix. We know that this is not invertible. When you go to your matrix menu and you say, let's get the matrix B, and then you say, well, let's try to find an inverse of that. When you hit enter, it's going to say error singular matrix. And singular, remember, is well, singular is a word that stands for does not have an inverse. Okay, singular matrix is a matrix without an inverse. Okay, so we can just quit that and clear. So that's what's going to happen there. All right, so this matrix does not have an inverse, so we call it a singular matrix. If you want, you can go ahead and do this one on your own. Just type it in, hit the inverse key. I'll push pause on the video and do that. All right, so hopefully you did that. Again, nothing fancy there. Oops, I lost it. But we get the matrix, the same exact inverse that we had before using that key on our calculator. All right, so that's the idea. So now we have three different methods for finding the inverse. We have the calculator key of -1, we have the row reduction algorithm, and we have the 2 by 2 formula. All right? You won't have to memorize the actual 2 by 2 formula. We will have to know the determinant, which we'll talk about more in chapter 3. But you should know the row reduction algorithm. At some point on the test, I'll ask you to use the row reduction algorithm in order to find the inverse. And by the way, the work I would want you to show, if for instance we did this, all I would ask you to do is write RREF, put in your matrix next to the identity matrix. That's getting there. So just put in this. Note that that's equal to the identity matrix in front. So you don't have to show your row reduction steps, is what I'm trying to get at. So just write that down. So write RREF big mess is equal to identity matrix this, and then you can say therefore my inverse is this part. Okay? So on the test, that's what I'd be looking for. At least one time, I'm going to have you use that row reduction algorithm to row reduce a matrix and use that to get the inverse. All right. Well, that is it for 2.2. Oh, I'm sorry. So using the row reduction algorithm, I'll have you do that once. Anytime I ask you to find an inverse, other than that, I'm perfectly fine with you using either of the any of the three ways that I showed. All right. So that is it for 2.2. That's the inverse of a matrix. That's kind of how to find it. In 2.3, we're going to look at some properties of inverses. So that's what we'll do in 2.3, and I'll see you next section.